This video is the second derivative test. Now, in addition to testing for concavity, we can use the second derivative to test for relative maximum or minimum. Doesn't happen very often. There's really no point in doing it. I'm not going to lie to you. The first derivative test is perfect for doing this, but we can use the second derivative test to do it. So this test is based on the fact that the graph of the function is concave up on an open interval containing c and f prime is equal to 0, then that point f of c has to be a relative minimum, right? So what we're saying is we're concave up, and this point at c, where the f prime is equal to 0, does this, then this has to be a minimum, right? Because it's the only way we're going to get that first derivative equal to 0. Now, similarly, if it's concave down on the interval, but equal to 0 at that point, then that's got to be a maximum, right? So, oops, wrong way. Here's our actual second derivative test. If we have a function and the first derivative equals 0, I don't have to plug in test points, okay? I just find the critical number c, and I evaluate the second derivative at that function, or at that point, that critical number. If the second derivative at the critical number is positive, then it's a relative minimum. If the second derivative at the critical number is negative, then that's a relative maximum, okay? If the second derivative is equal to 0 at that point, doesn't tell us anything, and we have to use the first derivative, all right? We can go back to the first derivative test. So let's actually use the second derivative here. So we're going to find the relative extrema. So we're going to start by finding f prime. So this gives us negative 15x to the fourth plus 15x squared. Okay, we're going to set that equal to 0. We're going to factor out the negative 15x squared. It's going to leave us with x squared minus 1. So we get that either x equals 0 or x equals 1. So these are our critical numbers. It's defined everywhere, therefore we don't have any non-differentiable points. We just have the points 0 and 1. Now, instead of making a number line, what we can do is just skip straight to what's the second derivative. Well, the second derivative would be negative 60x plus, or x cubed, sorry, plus 30x. So what we're going to do is we're going to plug in our critical numbers and see what happens. Well, when I plug in x equals 0, so I get f double prime of 0 equals 0 plus 0, I get 0. That means it fails at this point. Okay? If we plug in f double prime of 1, we get negative 60 plus 30, which is negative. Therefore, we're talking about we're concave down. Concave down means that we have a relative maximum. So we have a relative max. Now, since we don't know about 0, we can go back to the first derivative and look only at 0. Pick a number on this side and a number on this side. Negative infinity to 1. So it has to be less than 0, so negative 1 works, but it has to be between 0 and 1, so 1/2. Why does it have to be between 0 and 1? Well, because 1 was one of our critical values, right? Our critical numbers. So if I plug in negative 1 back to the first derivative, we get, this is positive, this is positive, that gives us 0. Aha! What happened here? I forgot something, didn't I? I hope y'all caught that. If x squared minus 1 gives us x equals plus or minus 1, right? So we need to test out negative 1 as well. So down here, if I plug in negative 1 gives us negative gives us positive 60 minus 30, which is 30, which is positive, which means we are concave up. which means we have a relative min. Now, this changes our 0 because now we're going to have to test between 0, -1, and +1. So -1/2 and +1/2. And we're going to plug them in over here. So if we use -1/2, -1/2 squared is +1/4. We get -15 fourths. -1/2 is 1/4 minus 1, which is a negative times a negative, which is positive, which means it's increasing here. If we plug in 1/2, we get -15. Basically, we do the exact same thing, right? Because the square eats it, so I still get a positive value. I'm still increasing. Therefore, that tells us that there's no relative max or min at that point. No max or min. All right. So we see that. We saw that the second derivative test failed at 0, 0. We used the first derivative test to determine that it is neither a relative minimum or a maximum. Here's the actual graph. Relative min, relative max, neither. So if you have any questions about the second derivative test, please just shoot me a reminder or ask a question in class.